This is Module 3 practice exam for college algebra, which is Math 1314 at Collin College. So the first question asks us to find the inverse function for f of x equals 3x minus 2. To find an inverse function, the first thing we're going to do is I like to rewrite it with y, and then I like to switch x and y. Because inverse, really fundamentally, that's what inverse is doing, is switching the x and y value. This is basically the answer already. The only thing we're going to do from here is we're going to solve it for y, because we want to get y by itself. So I'm going to add 2 to both sides, and then I have x plus 2 equals 3y. The last thing I'm going to do is divide both sides by 3, and then I've got y equals x plus 2 over 3. But instead of y, I'm going to write it as the inverse. So I'm going to say the inverse function is x plus 2 over 3. And that's the final answer for this question. This next one will be very similar. We're going to start the same exact way. We're going to put y equals, and then we've got log base 2 of x plus 3. Then, just like last time, we're going to switch x and y. And then what we need to do is rearrange it so that we can get y by itself. And if you remember, there's 2 little equations that you should have somewhere, but it's this. We've got log base b of m is equal to a power. Can always be rearranged as base to the power is equal to m. You can always go back and forth between these two, no matter the context. It's not always helpful to go back and forth, but no matter the context, if you have one of these expressions, you're always allowed to rewrite it as the other. So you may notice this one looks a lot like the logarithm version. So we are going to go ahead and rewrite it. Our base in this example is going to be 2. And then the power in this example is whatever it's equal to. So that would be x. So we've got 2 to the x is equal to. And then m is whatever is inside the parentheses, which in this case is y plus 3. Now we're almost there. To get y completely by itself, we're going to have to subtract 3 from both sides. And we end up with y equals 2 to the x minus 3. And again, to make it official instead of y, we label it as the inverse function equals 2 to the x minus 3. And this will be the final answer for this question. In number 3, we're asked to sketch the inverse. So what I like to do is pick a few points on this function. So like this point is going to be, it looks like 0, 1. Nope, 0, 2, 0, 2. And let's see, this point right here looks like 1, 3. And then this point over here maybe looks like 5, 6, 7, 8, 9, 5. So with those points labeled, what I'm going to do is switch the x and the y. So 0, 2 is going to become 2, 0. And then 1, 3 is going to become 3, 1. And then 9, 5 is going to become 5. Oh man, are these 2 different graphs? These are 2 different graphs somehow. 5, I will have to fix that, but 5, 9 is going to be off the charts. It'll be somewhere up here. But anyway, hopefully you kind of get the shape. The shape of the inverse is like this. It's the exact same thing, but we've switched x and y. Down here, we're asked to graph the function f of x equals 2 to the x plus 3 minus 4. What I like to do is separate out the parent function from the shifts and the stretches and the compressions and all of that. So first thing really easy to identify is that this is a shift. It's a shift down by 4. This is also a shift. It is a shift left by 3. And that leaves us with 2 to the x. So my parent function is 2 to the x. And in fact, I like to do that with a little table. So I'm going to say on one side, I've got x. On the other, I've got the parent. And the parent is 2 to the x. So some x values I could plug in. I usually like to do -1, 0, 1, and 2. So if I plug in -1, well, 2 to the -1 is going to be 0.5 or 1/2. Then we've got 2 to the 0, which is just 1. We've got 2 to the 1, which is 2. And then 2 to the 2, let me straighten this up just a little bit, which is 4. And that should be enough for me to graph my parent function. So -1 and 0.5, let's see. -1 is here, 0.5, that's right here. And then what's next? 0, 1. So 0, 1 is right here. And then we've got 1, 2. So 1, 2 is right here. And then we're going to have 2, 4, which is right here. So here's my original function. And if you know anything about exponential functions, you'll know that this is actually an asymptote at y equals 0. So now that I've got my parent function, I'm going to apply the two transformations. So the first thing I'm going to do is shift it left by 3. So if I take this guy and shift it left 3, it'll be 1, 2, 3 right here. This guy will be 1, 2, 3 right here. This one will be 1, 2, 3. And this one will be 1, 2, 3. My asymptote is not going to move because shifting this line left and right, not going to change it at all. The last thing I need to do is take every point and shift them down 4. So this one will be 1, 2, 3, 4. This one will become 1, 2, 3, 4. This one will become 1, 2, 3, 4. And this one will be, let's see, it's a little harder to see. 1, 2, 3, 4. And then I just connect those with a smooth line. And you may notice I'm going to need to move my asymptote down with it. And the asymptote will end up right here at y equals -4. So then I just like to label that blue is my final answer. For number 5, we are given a function. It says the population of India is modeled by the function f of x equals 1060 times 1.026 to the x, which gives the population in millions, and x is the years since 2000. So it says use this function to predict the population of India in 2028. So really all I have to do is plug 2028 into this function. But we have to do it carefully, so it says x is the years since 2000. Okay, so 2028 is going to be 28 years since 2000. So I'm going to have f of 28, which is equal to 1060 times 1.026 to the 28. And that's really all the math that I have to do. From here, I would just plug it into a calculator. So I'm going to pull up my calculator. And let's see, I've got 1060 times 1.026 to the 28. So 1060 times 1.026 to the 28. That gives me, I'm going to round it. It doesn't tell me what to round it to, but I'll round it to the nearest whole number. So I've got 2,175. So we will have 2,175 million. And that would be the answer to this question. All right, number 6 says you have $10,000 to invest. One bank pays 0.5% interest compounded quarterly, and a second bank pays 0.45% interest compounded monthly. Write a function to model each bank and then determine which one will result in a higher return on investment in 10 years. So I need two different functions. For my bank 1, they pay interest compounded quarterly. Quarterly requires this function. So we need a equals p times 1 plus or minus r over n to the power nt. For bank 2, actually it will be the same equation. The difference is going to be n. So bank 1 compounds quarterly, which means n equals 4. Bank 2 compounds monthly, which means n equals 12. It's the number of times it's compounded per year. So for the first one, A is what I'm looking for. 10,000 is the amount that I invest. It's going to be 1, and it'll be a plus because I'm getting more money. R is going to be, for bank 1, R is 0.5, so convert that to a decimal. I get 0.005 over N is 4 for bank 1. And then it's to the power of 4 times 10 because we're doing it for 10 years. Let me scoot this over so it's a little clearer. But bank 2 is going to be A equals, again, the principal is 10,000. It's still a plus. The rate is going to be 0.0045 over 12, and it's to the power of 12 times 10. And again, that's really all the math that I have to do from here. I'll just put it into a calculator. So let's see, I've got 10,000 times 1 plus, I'll put it in as a fraction, it'll be 0.005 over 4, because it's compounded quarterly, to the power of 4 times 10. So after 10 years, I have $10,512. So this one becomes $10,512.38. Over here, the other one will be very similar, but instead of 4, it'll be 12, and instead of 0.005, it'll be 0.0045. So we're going to do very similar thing, but instead of 4, it'll be 12 in both places, and instead of 0.005, it'll be 0.0045, and that should do it. And that will give me $10,460.19. So that is $10,460.19. So bank 1 is going to give me a higher return on my investment. Number 7, we're going to use the same idea, similar formulas, but this one says compounded continuously. For compounded continuously, we need this formula. A equals P times e to the RT. In this one, we are looking for A. P stands for principal. It's the original amount we put in, which is $2,050. Then E is a real number, so we leave it. R is 0.005, and then T is going to be 5. So we're just going to put this into our calculator. We've got 2,050 times e to the power 0.005 times 5. So we'll do 2,050 times e to the 0.005 times 5. And I get $2,101.90. So 2,101.90. Double check that. Yep. Now I'll put a dollar sign, and that's the answer. $2,101.90. All right, number 8, it says rewrite log base b of 32 equals 5 in its exponential form. Well, for that, we need these two equations that you should have somewhere in your brain. Log base b of m equals to p can always be converted into b to the p equals m. You are allowed to go back and forth between these two whenever you like. So right now, it's in a logarithm form. We're just going to write it as an exponential. So base is still going to be b. P is whatever it's equal to, so that's 5. And then m is what's inside the parentheses or what's inside the log, which in this case is going to be 32. And it doesn't ask us to solve it or anything. It literally just says rewrite it. So I'm going to change this to the right color and then put a box around it because that's our answer. This one's very similar. All it asks us to do is rewrite it as a logarithm. So right now it's an exponential, and 5 is our base. So I'm going to write log base 5 of, and then m is, in an exponential, it's what it's equal to. In a logarithm, it's what goes inside parentheses. So it'll be log base 5, 125 equals, and then it's equal to the power, which is -3. So all I've done is rearrange it, but that is all that I was asked to do, so I am finished. All right, number 10 says evaluate log base 3 of 1/9 without a calculator. I like to think of it as a sentence. Whenever you see a logarithm, it is asking, what power do you have to raise the base to? Raise the base to in order to get the result. So in other words, what power do we have to raise 3 to in order to get 1 over 9? Well, 3 to the what power is 1 over 9. Well, you may remember that 1 over really just means negative, so it's 3 to the negative something equals 9. And it doesn't take a whole lot of thought. Well, excuse me, it's 3 to the negative something. And the question is, what power do we have to raise 3 to get 9? It doesn't take a whole lot of thought to realize that the answer is 2. So the answer is -2. 3 to the -2 power equals 1 over 9. But of course, on the exam, you actually will have a calculator, so it's not even really necessary. You can just put it into your calculator if you need to. All right, number 11, we're asked to graph another function. So just like last time, I want to separate out my transformations from my parent function. So +2 is a transformation. It's going to be a shift up by 2. +4 is also a transformation. It is also a shift, but it is to the left by 4. What remains is my parent function. So my parent function is log base 3 of x. So I'm going to make a little table, and I'm going to have x, and then log base 3 of x. And for this one, there's not any like established x values that will always work. So you might just want to try some different things and see what you get. For example, if you plug in 0, you're going to get an error. You cannot take the logarithm of 0. There's no power that you can raise 3 to in order to turn 3 into 0. So the answer is it does not exist. Then you could try 1, and that's asking what power do we have to raise 3 to in order to get 1? Well, the answer is 0. You raise 3 to the 0 power in order to get 1. You could try 2. You'll get some weird decimal. I wouldn't worry about it. The next easy one is going to be 3, because what power do you have to raise 3 to in order to get 3? Well, that's just 1. And then one more that might be easy. It's not really on this graph, but you could do it, but it's 9. What power do you have to raise 3 to in order to get 9? And the answer is 2. So I'm going to graph what I have. I'll start with that does not exist. If x equals 0, it doesn't exist. We have a problem. And that on a graph looks like an asymptote. And then I can graph these points. So 1, 0 will be right here. And then we've got 2 decimal. I'm not going to worry about that. So we'll do 3, 1, which is right here. And then we've got 9, 2. Well, that's not really on my graph, but I'm going to put it out here anyway, because with the shifts, I think it might end up showing up. Then I can connect these points with a nice smooth line. And it looks something like this. Next, what I'm going to do is apply my transformations. So it doesn't really matter which order you do these shifts in, so I'm just going to shift it up first. So I'm going to take every single point and shift it up 2. So this one right now is at 2. It'll move up to 4. This one's at 0. It'll move to 2. And that's basically it. I've shifted everything up by 2. The last thing I need to do is shift every point left by 4. And that's where this guy will pop up. So right now it's at 9. If I shift 9 left 4, it'll be at 5. This guy, shifted left 4, is going to be 1, 2, 3, 4. This one will be 1, 2, 3, 4. And is that it? Oh, that's it. Oh, and my asymptote. My asymptote, shifted left 4, will end up right here. And then I connect these things with a nice smooth line. And as always, I like to label it, which one is my final answer. In this case, my final answer is in green. All right, number 12, it says simplify this expression, log of base 10, it's not written, but it's base 10, of 2x plus 5 minus log of x. And you may remember that when two logarithms are subtracted, their arguments are divided. So you can combine it into a single logarithm with 2x plus 5 divided by x. And that's it. There's not a whole lot else we can do. There's not a whole lot else we can do. It's combined into one expression, and that's the final answer. This one is a similar idea, but it's going to be the exact opposite implementation. So we've got the log of the fifth root of x over y. And I always like to rewrite my roots as powers because powers are a lot easier to deal with when we're doing logarithms. So the fifth root is the power 1 over 5. And you may remember, but you can take this power and move it to the front in a logarithm. So I'm going to have 1/5 times the log of x over y. And now we've got x divided by y, which you may remember just from the previous one, divided by, is you can change to a subtraction between two logarithms. So this 1/5 will stay, and then I'm going to have the log of x minus the log of y. And if you like, you could distribute the 1/5, but it's not really going to matter either way. This is going to be your final answer. All right, number 14 says solve the equation 3 log base 2 of x minus 1 equals 5 minus log base 2 of 4. Now, our goal is always going to be reduce the number of logarithms or reduce the number of exponentials in the equation. At most, we want 1 on each side and nothing else. We don't want a bunch of numbers. So like this 5 minus and this 3 are both problems. We want logarithms by themselves. But here's what I notice about the best way to get rid of a logarithm. This one right here is actually very easy to evaluate. Log base 2 of 4 is asking, what power do you have to raise 2 to in order to get 4? And the answer is the second power. Log base 2 of 4 is 2. So we could just write 3 log base 2 x minus 1 equals 5 minus 2. And we are already down to 1 logarithm. From here, all we have to do is we want to move all the numbers over to one side. So first, I'm going to do 5 minus 2. And then, because I want to get the logarithm by itself, I'm going to divide both sides by 3. And then I get log base 2 of x minus 1 equals 1. Now I can rewrite it as an exponential. My base is 2, my power is 1, and my argument is x minus 1. Then I just add 1 to both sides. And 2 to the 1 is 1. 2 to the 1 is 2, plus 1 is 3. And that should be it. I get 3 equals x. Now I should double check this because logarithms have a restriction. You're not allowed to take the logarithm of a negative number. So I really should take this 3 and I should plug it back into my original equation. So if 3 goes right here, I have 3 minus 1. Well, 3 minus 1 is just 2. That's not a negative number. There's nothing illegal about that operation. And if you work it out, it actually solves the equation very nicely. So I've checked my answer. It does not give me a negative, so I'm going to give myself a check mark and put a box around it. X equals 3. Number 15, same strategy as the last one. We really want to reduce the number of logarithms. At most, we want 1 logarithm by itself on each side. So the first thing I'm going to do is I'm going to combine these two. And to combine them, I use the property of logarithms that says if you've got an addition between 2 logarithms, you can change it to a multiplication of their arguments. So I'm going to have the natural log of x minus 4 times x plus 1 is equal to the natural log of x minus 8. Then, because I've got 1 logarithm on each side by itself, what I can do now is undo both of them at the same time. So you may remember, but the way to undo a natural logarithm is use an exponential. Those two things are inverses. Logarithms undo exponentials, exponentials undo logarithms. In this case, you might remember, but ln is really just log base e. So the way to undo it is do e to the power. So I'm going to raise e to the power on both sides. And then e to the and ln of cancel each other. So e to the and natural log of will cancel each other. And I'm left with x minus 4 times x plus 1 equals x minus 8. From here, I'm going to FOIL. So I'm going to multiply. And when I do this multiplication, I get x squared plus x minus 4x minus 4 equals x minus 8. If I combine my like terms, I have x squared minus 3x minus 4 equals x minus 8. Then I'm going to subtract x from both sides, and I get x squared minus 4x minus 4 equals negative 8. Then I'm going to add 8 to both sides, and I have x squared minus 4x plus 4 equals 0. Now I can factor this, and to factor it, we really need two numbers that multiply to be 4 and add to be negative 4. The two numbers that I can think of that do this are negative 2 and negative 2. So this factors as x minus 2 times x minus 2. And normally we would split that up into two equations, but they're the same equation. So this really just gives us x minus 2 equals 0, which means if I add 2 to both sides, x equals 2. But as always, we need to check our answer because logarithms have restrictions. There's the potential for problems to occur. So I'm going to take 2 and plug it back in over here. So if I plug in 2 right there for x, 2 minus 4 is going to be negative 2. You cannot take the logarithm of a negative number. So the natural log of negative 2 is going to be an error. You will have a problem, which means this answer did not work. But it was the only answer we got. So our conclusion is this problem has no solutions. Number 16 asks us to solve this equation. E to the x plus 4 equals 1 over e to the 2x. And just like with the logarithms, our goal is to simplify and reduce. We want to get rid of all the extra numbers. We want to, at most, have one exponential on one side and a matching exponential on the other side. So really the problem here is this 1 over business is kind of in the way. If we could get rid of that, then we'd have an exponential, and that would be perfect. And you may remember, but 1 over just means negative exponent. So I'm going to have e to the x plus 4 equals e to the negative 2x. Now, I've got one exponential on each side by itself. So what I can do is undo the exponential on both sides. Well, to undo e to the, you use natural log. So I'm going to take the natural log of both sides. Natural log and e will cancel each other. And we're left with x plus 4 equals negative 2x. I'm almost finished. From here, I'm just going to subtract x from both sides, and I get 4 equals negative 3x. And then I'm going to divide both sides by negative 3. And I end up with x equals negative 4 over 3. Now, I can plug this one back in and check it, but because it's an exponential, there are no restrictions. You're allowed to have any kind of number in an exponent. You can have a negative, you can have a fraction, you can have a positive, it does not matter. So because there's no restrictions, it's actually not necessary to check it. If you wanted to, it's never a bad idea, but in this case, it will work. Number 17 asks us to solve this equation. 3 to the 2x plus 3 to the x minus 2 equals 0. Now you might think that at first glance, and actually you should check this, you should always check this, is for a way to combine these guys and get rid of everything else. The real problem here, though, is there is no way to combine two exponentials that are added. These are two different exponentials, and there is a plus in between them. There is no way to combine that. So we use our backup option. Our backup option, and the only other strategy we've really learned, is to treat this like a quadratic. A quadratic means that we've got something squared plus something in the middle, and then usually there's a number. In this case, the number is -2. Now you're allowed to have coefficients here and here, but the coefficients are not required. So if you copy basically this expression down below, you might notice that you would have 3 to the x inside these parentheses. So really this is exactly the same as what's below. I just have 3 to the x squared instead of 3 to the 2x. Oh, I guess I should just be consistent. All right, so we've got 3 to the x squared plus 3 to the x minus 2 equals 0. And I like to rewrite this using another variable. So I really prefer to write this as y squared plus y minus 2 equals 0, because it's just a little easier for my brain to see what's going on. Now from here, this is a quadratic, so we're going to treat it exactly like we would a quadratic. We're factoring it, so we're looking for two numbers that multiply to be -2 and add to be 1. And if I think about this for a minute, 2 and -1 do the trick. 2 times -1 is -2, and then 2 plus -1 is 1. So this is going to factor as y plus 2 and y minus 1. So that means we've got y plus 2 equals 0 or y minus 1 equals 0, which if we solve each of them, we get y equals -2 and y equals 1. But you may remember, it wasn't really y, it was 3 to the x. And then from here, to solve these two equations, we can rewrite them as a logarithm. So our base is going to be 3, and this one, our argument is -2. Over here, our base is going to be 3, and our argument will be 1. And you might notice, actually you can notice in this step, if you are paying attention, but this has no answers. You cannot take the logarithm of a negative number. So that equation will give us no solutions. But over here, if I asked you, what power do you have to raise 3 to in order to get 1? You might be able to answer the power of 0. So in this equation, x is equal to 0. And it is the only valid answer. And because our equation was in exponentials, there's no need to check our answer unless you just want to be really certain. So x equals 0 is the final answer for this question. For number 18, we want to solve this equation. 5 to the 2x times 5 to the 4x equals 125. As always, we're going to try to combine because we really want, at most, one exponential on each side. Right now we have 2 exponentials on this side, so let's combine them. 5 to the 2x times 5 to the 4x, well, since they're multiplied, we can add their exponents together. So if we add 2x plus 4x, we end up with 6x, and we have 5 to the 6x equals 125. From here, we can rewrite it as a logarithm. We've got log base 5 of 125 is equal to 6x. And you can check it in your calculator if you need to, but if I said, what power do you have to raise 5 to in order to get 125? You might know that the answer is 3. And if you didn't know, you can always do it in your calculator. From here, I'm going to divide by 6, and I'm basically done. I get x equals 3 over 6, which simplifies to 1/2. Number 19, the half-life of lead is 22 years. How long will it take for a sample of this substance to decay to 80% of its original value? I'm going to start with my equation. So my equation is this guy. We've got 1/2 to the t over h, where h stands for the length of the half-life, t stands for the time that has passed. This one is the original amount, and this one is the final amount. So there are many ways to do this one, but what I'm going to do is say, I'm going to pick a starting amount. So let's say we start with 100 grams. 80% of that is going to be 80 grams. Now, you didn't have to measure it in grams. You could have measured it in pounds or ounces or whatever. But I just like to pick numbers that are concrete to plug them in. So if it's decayed to 80%, that means it's gone from 100 to 80. So I'm going to plug in 80 is our final amount. 100 is our initial amount. And then we've got 1/2 to the t is what we're looking for. And the length of the half-life is 22. From here, I need to divide both sides by 100. And then I get 0.8 equals 1/2 t over 22. Then, because this is an exponential, I can rearrange it as a logarithm. So I can write log base, and then my base is 1/2. My argument is 0.8, and it's equal to t over 22. Then I can just multiply both sides by 22, and I have t equals 22 times the log base 1/2 of 0.8. And to figure out what number this is, I can put it into my calculator. So I'll have 22, and then to put in log with a different base, you just go math and then scroll up until log base. And then I'll put in 1/2. So log base 1/2 of 0.8 is equal to 7.08. So this is roughly 7.08. So as a sentence, it will take 7.08 years for lead to decay to 80% of its original value. And I'm running out of space, but that's the sentence. For lead to decay to 80% of its original value. Done. All right. Number 20. We've got a bird species which is in danger of extinction and has a population that is decreasing exponentially. 5 years ago, the population was at 1,400, and today only 1,000 birds are alive. Write a function to model this situation. So I'm going to call it P of t, where P stands for population and T stands for time. So the population is equal to, and it's going to be equal to the original population. We'll call it P0. That means the population at time 0 times 1 minus the rate of decrease. We don't know what the rate is, but we'll find it, to the power of t. This is very, very similar to your investment problems. It's very similar to your half-life problems. It's actually exactly the same as your investment problems, just with different letters. But to solve this one, I'm going to plug in the numbers that I have. So let's see. 5 years ago, so that means t equals 5. The original population was 1,400. So 1,400 is what goes here. And as we said, t was 5. And then 1,000 is what it's equal to now. So this is enough for me to find r. R is what's missing in this equation. So what I'm going to do to solve for r is, it starts the same way most of them do. You're going to divide by 1,400. And then I get, well, this is 5 over 7. I'm just going to leave that as a fraction. It's equal to 1 minus r to the 5. Now, we don't need to rearrange this as a logarithm because there's no variable in our exponent. It's just a 5. So really what we can do is take the 5th root of both sides. So I've got the 5th root of 5 over 7 is equal to 1 minus r. And honestly, I mean, you could subtract 1. I'll go ahead and subtract 1. We may as well. So r, negative r, is equal to the 5th root of 5 over 7 minus 1. And then I got to divide by -1. And I get r is equal to the 5th root of 5, negative 5th root of 5 over 7 plus 1. So this I'm going to solve in my calculator. Negative fifth root. Just for convenience, I'm going to put it in as to the power 1/5. So we've got 5 over 7, and then fifth root, fifth root means to the power 1/5. So there's the negative fifth root of 1/7 plus 1. And I get 0.065. So this is approximately 0.065. Which means if I plug it back into my original equation, the population of birds is equal to, well, P0 we already know is 1,400. And then 1 minus 0.065, 1 minus this number is going to be 0.935. 0.935 to the power of t. Here's a good function to model this situation. The second part of the question says, when will the population drop below 100? And I'm running out of room here, so we will see what we can do. But to say the population is below 100, I'm just going to put 100 equals, because the population has, we'll figure out when the population hits 100, and that's right after that is when it drops below. And then it's going to be 1,400 times 0.935 to the power t. To solve this equation, I divide both sides by 1,400. And then I get 1 over 14 equals 0.935 to the power t. I can rewrite this as a logarithm, and it's log base 0.935 of 1 over 14 is equal to t. So that will be, let's see, we're going to do log base 0.935. It'll be rounded, but that's okay, of 1 over 14. And that is 39.27. Let's just round it to the nearest whole number. This is approximately 39. So 5 years ago, the population was 1,400. 39 years after that, which is 34 years from today, the population will drop below 100. So as a sentence, trying to fit it in here somewhere. Not sure I have room, but the answer is 34 years from today, the population, I'm just going to say the population will hit 100. And that is the answer to this question. All right, number 21, the last one. This says you invest $5,000 in an account with 2% interest compounded quarterly. How long will it take for the account to reach a value of $10,000? Well, I'm going to use this equation. Amount equals principal times 1 plus or minus, but in this case it's plus, r over n to the power of nt. And in this equation, the amount that we have after time has passed is 10,000. The principal is 5,000. 1 plus r is 0.02. N is 4 because it's compounded quarterly. And then it's raised to the power of 4t. First thing I'm going to do is divide by 5,000. And I get 2 is equal to 1 plus 0.02 over 4 to the power of 4t. And I can really simplify that. That's just 1.005. And now, because it's an exponential and I've got a variable in my exponent, I can rewrite it as a logarithm. And I get log base 1.005 of 2 is equal to 4t. So the last thing I need to do is just divide both sides by 4. And I get t is equal to log base 1.005 of 2 divided by 4. And that I can solve in a calculator. So I'll do math log base 1.005 of 2 divided by 4. And I get 34.74. So T is 34.74. This interest is compounded quarterly, which means, and T is measured in years, which means it will take 34 years. And then because it's compounded every quarter, we just need to know how many more quarters. 34 years and 3 quarters for the account to reach $10,000. And that should do it.